As human beings, we are instinctively drawn toward the grandeur of the natural world, to spectacular displays that inspire us with their magnitude and power. During moments like these, we are understandably filled with a genuine sense of awe. Yet nature's most stunning revelations aren't always defined by sheer force or physical scale. For often, in secluded corners of our planet, many of Earth's greatest wonders take center stage. Wonders of rare beauty and complexity, creativity and design. Wonders born on the gossamer wings of an insect weighing less than an ounce.
As you watch a butterfly, to describe what you're looking at, you can't really put it into words. And I said to myself, I want to be part of that. That is the coolest thing. That's biology, it's also magic.
When you hold a living butterfly in your hand for the first time, maybe you've netted it or you've picked it off a flower or something, and here's this incredibly beautiful organism, intricately shaped with its feet and antennae and all these things moving at once.
Every one of these 20,000 species have different color patterns, and every one of them has different shaped wings. The diversity is just so magnificent. If I was the greatest artist in the world, there was no way I could come up with all of these patterns. I mean, it would be just absolutely impossible.
If you open the work of a lepidopterist, someone who studies butterflies, somewhere in that writing, you're going to find the language of astonishment. The fact that it goes through a caterpillar stage and then becomes this mysterious chrysalis, out of which this flying creature emerges, has captured the imagination of people since antiquity.
Throughout history, butterflies have touched the human mind and soul on levels both scientific and philosophical. 3,500 years ago, Egyptian artists studied their anatomies and then rendered them as icons of beauty and perfection of form. In Aztec and Mayan folklore, the insect symbolized life and death. And to the ancient Greeks, Psyche, the word for butterfly, literally meant the soul. Today, terms like magical and miraculous are often used to describe their mysterious life cycles. For almost every butterfly, it is a cycle that begins, often hidden from the eyes of the world. Depending upon its species, a female butterfly can lay hundreds of eggs during her brief lifetime. Each initiates an extraordinary process of growth and transformation.
The eggs are remarkable in themselves. They have species-specific architectures, some of which are just astonishing. For instance, if you look at a monarch egg, it has a beautiful symmetrical structure. It looks like a little miniature dome or cathedral.
Ranging in size from a pinhead to the width of a child's fingernail, each egg is attached to a plant by an adhesive fluid secreted by the butterfly. They are lined with a coating of wax that helps keep them moist and viable. Each egg is deposited on a specific species of plant called a host. These host plants are the only source of food a butterfly's offspring will eat. So accurate identification of their leaves and branches is crucial, and the females are well equipped for the task.
The perception that they have of the odor of those plants is just overwhelming. So they can find those plants for miles, and then once it gets near its host plant, it can tell that the odor is getting stronger and stronger. Then it begins to focus on leaf shape. Instinctively, it knows what leaf shape its host plant has. And it begins to taste. And it tastes with its feet, with its forelegs. They drum the leaves, they scratch the leaves, and then they use their proboscis to taste the scratch. They also smell with their antennae. So they've got the legs, they've got their proboscis, they've got their antennae. They have all these mechanisms to make sure that it's the right plant. If it's the wrong plant, their caterpillars are going to die. Butterflies just don't make mistakes. I mean, it's just amazing. It's one of the greatest wonders of nature to watch how this female can do all of this from such great distances.
In many species, the eggs hatch within a week. Then the newly emerged caterpillar, or larva, wastes no time embarking on the second stage of its journey to adulthood.
We call them eating machines because that's their only purpose in life, is to just eat and grow, eat and grow.
A really hungry, busy caterpillar, you can actually hear it eating. It sort of reminds you of corn on the cob, because it bites along and then it bites along some more.
It's just munch, 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 munch. Slice and chew, slice and chew, to build up the raw materials for the next stage of life.
A caterpillar could gain in weight so fast that it would be eating its own weight in leafy material every day.
Equipped with powerful jaws and a digestive tract that extends the length of its body, this stomach with legs can multiply its birth weight more than 3,000 times in less than 2 weeks.
To show you how remarkable this weight gain is, imagine you had an 8-pound human baby and he multiplied his weight 3,000 times as he was growing. That would be a 24,000-pound child. That's a big kid.
A caterpillar's growth is punctuated by violent surges of transition called molts.
Imagine the outer skin of a caterpillar as being sort of like a wetsuit. It's got a little bit of stretch to it, but limited. It's waterproof, so they don't dehydrate. Now, as the caterpillar grows, it fills out that wetsuit, and eventually it reaches a point where it can't grow anymore, and it has to make a new, larger version on the inside.
A molt begins when a caterpillar spins and then grasps a silk pad, anchors its body securely with small barbs on its legs, and splits its skin near the capsule covering its head.
There are sensors in the cuticle, in the skin of the caterpillar, that are strain detectors. They detect the amount of pressure or strain being put on the skin. And when that is too great, they send a signal to the brain of the caterpillar, which then releases a hormone that causes molting.
A caterpillar will undergo 4 or 5 molts. Its rapidly growing body is composed of 2 distinct cell populations: the larval cells that form all of its organs and enable it to function, and the imaginal cells that ensure its future as a butterfly.
In the later instars of the caterpillar, one can begin to see what are called imaginal discs. Now, these are the precursor cell populations for what will become wings and legs or sensory structures in the adult.
Most of these imaginal cell clusters develop in pairs and are positioned throughout the caterpillar's body in locations that correspond to the organs they will eventually help form in the adult.
Imaginal discs are precursors that are there and waiting. They're set aside to make adult structures. And at a certain point in development, those cells are triggered to start to grow.
As the end of the larval stage approaches, the caterpillar stops eating, finds a secluded spot, and spins another silk pad. When finished, it attaches itself with a pair of claspers on the end of its body, then hangs almost motionless.
It will hang there for a day or so, usually in a J position. All kinds of chemical reactions occur within that caterpillar. It changes color, and you have no idea what's going on inside there until all of a sudden it pumps the fluid so that the skin begins to split.
The caterpillar's final molt marks the beginning of the third stage of a butterfly's development and the appearance of a remarkable structure called a chrysalis. As the old skin is pushed away, the cremaster, a thin extension on the top of the chrysalis, works its way into position to permanently grasp the silk pad. With a scanning electron microscope, the cremaster is magnified more than 500 times.
The caterpillar has microscopic hooks on the cremaster, and it attaches those hooks to that silk pad that it puts on the bottom of a leaf or twig. And it begins to spin, and this caterpillar spins and spins and spins because it wants to get rid of that old skin that it has.
During the hour that follows, the chrysalis hardens and takes its final form as one of the most fascinating processes in nature is set into motion. The metamorphosis from caterpillar into butterfly.
What you see in a chrysalis is not a shapeless mass, but in fact, something very much like a mold for the adult butterfly.
You see the wing pads where the adult wings are going to form, and you see the head and the compound eyes appear, visible through the outer case of the pupal shell. Abdominal segments are very clearly separated from the thoracic segments where the wings are going to be attached. All of this is astoundingly new compared to the caterpillar, where everything looked sort of the same down the whole length of the body.
This transition from an earthbound plant-eating arthropod with limited vision and mobility into a beautiful winged insect that feeds on nectar, navigates with exceptional senses, and can fly 50 miles in a day is truly a marvel of the natural world. Exactly how it happens is still very much a mystery. Yet innovative research at the level of molecules and cells provides intriguing new clues.
There is some continuity of tissues from caterpillar to adult butterfly, but most of what was there in the caterpillar is going to disappear and be turned into new structures that have no analog in the caterpillar. For instance, there's nothing like the compound eye of the adult butterfly present in the caterpillar. There's nothing like the proboscis present in the caterpillar, or the long articulated legs in the caterpillar. So these are all novel structures that are going to be built.
In a metamorphic insect, what you've got is two body plans. You have to first form one functional body plan, and then you have to switch gears and you have to take and form a new body plan. I am amazed by development when it goes from egg to caterpillar, because it's such an intricate process. But then you have to enter into the chrysalis stage and you have to get it right again. So it's like the problem squared.
The creation of a butterfly begins with the partial destruction of the caterpillar. Inside the chrysalis, larval cells that form the caterpillar's limbs and organs are systematically digested and broken down.
You've got to get rid of or digest the caterpillar tissues. They won't work for the adult. In fact, the cells themselves disappear, but then their components are recycled and are turned into a kind of soup out of which the adult structures will be built.
Throughout this process, the imaginal cells, the foundation of the adult insect's body, are preserved to differentiate and multiply.
Now, cell death is programmed. It's not something that happens by accident. If you kill the wrong cells, you're in deep trouble.
It's very carefully engineered. You're going to save some of the cell populations, so you got to know where you're going to end up before you start. You don't want to digest everything, just things that need to be eliminated. Then the imaginal discs rapidly begin to proliferate, and you can trace a continuous pathway into the pattern on the wing.
This timeless drama of death and renewal is performed in the seclusion of the chrysalis, without audience or applause. During the past 2 decades, scientists have worked diligently to pull back the curtain.
I've been at this about 15 years, and the possibility of somehow getting in there to photograph what's inside a chrysalis, that question was out there all along, and it occurred to me that magnetic resonance imaging might be perfect tool to use to see what goes on inside a chrysalis.
The challenge of visually documenting a butterfly's development led biologist Richard Stringer to Duke University and its Center for In Vivo Microscopy. There, over a 10-day period, monarch butterfly chrysalises were scanned throughout a complete cycle of metamorphosis. Each scan visually sliced the chrysalis into more than 200 sections. 8 hours into the first day, Stringer observed significant changes.
Even though it was very early in the development of the chrysalis, you could already see things forming that were going to be part of the butterfly, including the head, including the brain, including leg muscles, wings, antennae. The longer it's scanned, the more detail you get.
Stringer's magnetic resonance data was later used to create a 3-dimensional dissection of the butterfly's body as it took shape within the chrysalis. On day 1, the caterpillar's massive digestive tract is still nearly full size. By the 10th day, hours prior to the butterfly's emergence, the tract has been totally reconstructed. It is now about 25% of its original volume, ideal for the adult insect that will feed almost exclusively on nectar. During this transformation, the butterfly's reproductive organs, non-existent in the caterpillar, develop completely, while its tube-like heart is remodeled to fit and function within the abdomen of the butterfly. In the front of the chrysalis, dramatic anatomical changes continue. The caterpillar's simple eyes, capable only of discerning darkness and light, are replaced by large, complex organs of vision. A muscular system that will power flight and locomotion is built from both imaginal and recycled larval cells. The butterfly's 6 legs, 2 antennae, and feeding tube are individually formed while tightly compacted into a mass against the wall of the chrysalis. And 4 wings, each with elaborate networks of veins and scales, are shaped, decorated, and refined in less than 2 weeks.
It's like a different organism. And as the week goes on, transitions have to take place in the heart. Transitions have to take place in the antennae. Transitions have to take place in the reproductive organs. You got a big orchestra in there. You got a great big orchestra, and you got a conductor, some conducting force that's responsible for it all. I can say without any doubt that it was the most amazing thing I'd ever seen.
Caterpillar into butterfly. The transformation to an entirely new way of living is nearly complete. During the first moments after emergence, the butterfly makes final preparations to fly and eat as it finishes construction of its proboscis and wings.
The proboscis is a straw-like tongue, hollow in the middle, and the butterfly has muscles in its head which can create a suction, a sort of a suction pump, and draw nectar up.
Within the chrysalis, the proboscis developed as 2 separate pieces. Now, immediately following emergence, the butterfly must assemble them into a single unit, or die of starvation.
It's 2 half straws. There's a channel on one side and has to get it into the channel the other side. You'll see two little appendages on their head called palpi, and those palpi seem to protect the proboscis and help that proboscis get put together.
As the butterfly knits together the proboscis, its wings also take on their final structure.
When the butterfly comes out of the chrysalis, the wings are like velvet. They're soft, they're pliable. There's veins, the wings are filled with veins.
What the butterfly does is, using its abdominal muscles, pumps hemolymph fluid into the veins, into the wings, and they quickly expand to their full size and shape.
Each of the butterfly's 4 wings is covered with thousands of microscopic scales that are positioned like shingles on a rooftop. These scales are not only arranged for aerodynamic efficiency and spectacular patterns, they also act as solar panels, collecting heat to warm the flight muscles of the cold-blooded insect. A butterfly's eyes are also formed from a vast network of component parts. Thousands of hexagonal light receptors work in unison to produce a mosaic view of the insect's environment. While the spherical shape of each compound eye creates a field of view more than 180 degrees wide.
They have 4 color vision systems, pigment systems, which enable them to see from the ultraviolet to infrared. Butterflies have better color vision than humans.
The butterfly's antennae, legs, and feet complete its sensory system. The antennae that control balance and equilibrium in flight recognize the aromas most important to the butterfly. Their clubbed ends are covered with scales that can detect the scent of a host plant or prospective mate more than a mile away. A butterfly has 3 pairs of jointed legs with scales and fine hairs that sense vibrations and possibly sound, while its legs and claws are lined with nerve cells that react upon touch to a leaf's distinct flavor. This heightened sense of taste is activated whenever the insect scratches the surface of a plant.
Some of the best biologists and chemists in the world are now studying the process of metamorphosis on a series of new levels, trying to integrate this with the advances and techniques that we have from molecular biology to modern imaging systems.
In the case of butterflies, it's like a fine piece of art. You can appreciate it at a sort of technical level in terms of what was required to get the pigment on the canvas and so forth. But what's going on is so much richer than that and so much more significant than that.
We know just the bare outlines of a few of the processes involved for metamorphosis. It's a mystery. It's like a black box. Input larva, black box. Output butterfly. What happened? What happened?
We only know a thousandth of what's going on inside those insects, inside that pinhead brain, and all the things that it can do, the way it can navigate, the way it can migrate, the way it can find the females, the way it can find the plant. It's one of the great wonders of the world.
As science probes deeper into the life cycles of the 20,000 species of butterflies known to inhabit the Earth, one story stands unique from any other. It is an epic saga that unfolds across a continent and a journey to the heart of the beauty and mystery that epitomize metamorphosis. For more than 30 years, researchers from throughout the world, including biologist Thomas Emmel, have traveled to a secluded forest to study a phenomenon unparalleled in nature: the monarch butterfly's migration to Mexico.
I've gone down every year since 1981, and many years made a number of trips, 2, 3, 4 trips a year. Here's a butterfly species that does something truly spectacular. Just imagine 300 million monarchs in one site that have flown 2,500, 3,000 miles to end up in these tiny 12 areas that still exist in the transvolcanic range of south central Mexico.
The monarch's migration begins each September when most of the North American population east of the Rocky Mountains departs for central Mexico. Their journey can span more than 2,500 miles and is critical for 2 reasons. Monarchs are tropical butterflies unable to endure the freezing winter temperatures of the Midwest and Canada, and their life cycle depends upon the milkweed. More than 100 species of milkweed grow throughout the United States during the spring and summer. It is the only plant a female monarch will select to host her eggs. Milkweed leaves contain cardiac glycosides, toxic chemicals that can cause illness or death. After hatching, the caterpillar eats the plants and stores their poisons in its outer layer of skin. Then during metamorphosis, the glycosides are transferred from caterpillar to adult. And whenever the monarch spreads its wings, their distinctive pattern sends a warning to predators. Don't eat me. I taste terrible. Like the monarch, milkweed cannot survive the harsh North American winter, and by the end of August, it goes to seed.
And at that point, the monarch stops all reproductive activity. If it's a female, no more eggs. If it's a male, no more sperm. They still feed, are active, but they show no interest in sex or reproduction.
With no milkweed for their eggs until spring, the monarchs devote themselves entirely to preparation for a transcontinental flight. They spend the final weeks of summer feeding on nectar to build reserves of carbohydrates and fats, the fuel for their journey. Monarchs born in the spring or early summer have a lifespan of only 2 to 4 weeks. But the generation that emerges in August is genetically programmed to live up to 9 months, a provision crucial to survival.
The last generation of the summer, the one that's going to live all winter and into the following spring, is really an interesting problem for biologists, because here you have 2-3 generations preceding that generation where the adult lives at most 2 weeks, 3 weeks, 4 weeks, and then dies. And now all of a sudden, a generation's produced that's going to live 9 months, 9 times as long. It's thought that there's a genetic difference comprised of about 6 genes that are unique in this generation that enable it to live that long.
Often called the Methuselah generation, their longevity will enable the butterflies to fly south for 8 weeks, endure 4 months of winter, and then start the return trip north to establish a new generation of monarchs in the spring. With the approach of autumn, the angle of the sun at midday drops below 56 degrees. The shortening days are the butterflies' cue to begin their migration. A network of sensory organs will enable them to navigate throughout the journey south.
The question is how the butterfly figures out what direction to go. We're looking at several things. The butterfly is able to detect day length through tiny organs on its antennae. It's able to detect the position of the sun above the horizon by visual senses, and also compensate with a biological time clock in its brain for the movement of that sun from early in the morning on the eastern horizon to the western horizon at the end of the day when it sets. So they're moving south, following the sun's directions, and they're adjusting their flight each day.
From as far north as Canada, Michigan, and Maine, the monarchs travel an average of 50 miles a day as they glide on currents of warm thermal air. By mid-October, their primary migration routes converge, as most of the butterflies funnel into southern Texas before crossing the border. Some, however, take a more direct route across the Gulf of Mexico. In late October, on evenings following the passage of a cold weather front, monarchs descend upon the gas and oil rigs throughout the Gulf. Perhaps attracted by the lights, the butterflies interrupt the longest non-stop leg of their journey. Here, among the pipes, ropes, and heavy machinery, they rest for the night. In 1993, biologist Gary Ross and a team of volunteers documented monarchs on more than 20 platforms during a 2-week period. At daybreak, the butterflies warmed their bills, calculated their bearing by the position of the sun, and then resumed their journey. After crossing the southern border of Texas, the eastern monarch population merges into a flyway about 50 miles wide. During this leg of their migration south, they follow the geography of the Sierra Madre Oriental mountain range. Then, near a region called the Sierra Gorda, they abruptly change direction and cut through a pass heading southwest toward the interior of Mexico.
And there they find the end of the desert and the start of a transverse mountain range that runs west-east, and that's the transvolcanic range.
The transvolcanic is the tallest range in Mexico. Its mountains contain rich deposits of heavy metals that may play an important role in the monarch's navigation.
Gold, iron, manganese, copper, all of these metals created an anomalous magnetic field. And this seems to be important in bringing the monarchs in, because the monarchs have tiny particles of magnetite, the mineral magnetite, in their body at the base of the wing and in the thorax and abdomen. And these are believed to help them navigate to precisely this mountain range, because there's a very strong magnetic anomaly as one approaches this range due to all these heavy metals near the surface. So the particles of magnetite rotate like a little bar magnet inside a cell, and that cues the monarch that needs to head in a certain direction.
Until late in the 20th century, the only people to ever observe the butterflies' arrival in Mexico were the farmers and miners who lived and worked in these volcanic mountains. Then, on January 2nd, 1975, in a forest 70 miles west of Mexico City, a spectacular discovery opened the door for the rest of the world. Millions of monarch butterflies had gathered in a forest of Oyamel firs 10,000 feet above sea level. Frederick Urquhart, a Canadian biologist who devoted his career to the search for this colony, described it as a glorious, incredible place where butterflies swirl through the air like autumn leaves, shimmering against the mountain sky and drifting across our vision in a blizzard of orange and black. Science now glimpsed the true magnitude of the eastern monarch's migration.
One of the really remarkable things about this migration is that all of these individuals have never made the trip before. It was their grandparents or great-grandparents 2, 3, 4 generations ago. They have no leader who's made the trip before, unlike whooping cranes or sandhill cranes. They don't have an older, experienced adult to take the lead and show them where to go, where to stop at night. But in the end, it ends up on the very same trees, same area, same slope of the mountain that its parents and grandparents left from the previous year.
Since 1975, a dozen permanent overwintering colonies have been discovered in these mountains. Each maintains a critically balanced microclimate that helps sustain the monarchs until spring. Average temperatures in the colonies range from 35 to 60 degrees Fahrenheit, warm enough to protect the insects from freezing, and cool enough to minimize their expenditure of energy. For more than 4 months, hundreds of millions of butterflies live in a state of semi-hibernation while slowly consuming the reserves of nutrients they accumulated during the summer. The bark and needles on the fir trees provide stable footholds, and by flocking in roosts several layers deep, they can endure days or weeks of inclement weather. With the arrival of spring, the insects prepare to depart the overwintering sites. After the sun warms the colony, the monarchs leave their roosts for a few hours each day. They travel short distances in search of nectar and water that will nourish them during their journey north. At lower elevations, they feed on the new bloom of wildflowers and draw moisture from the damp grass and the rivulets that run down from the mountains. The lengthening days also trigger a change in the monarch's biology. In early March, the butterfly's reproductive organs become active as the males produce sperm and the females eggs. After mating, they leave the colonies and head north, ready to establish a new generation. The monarch's departure from Mexico coincides with the appearance of a new crop of milkweed in southern Texas. When the females find the host plants, they lay their eggs. Their life cycle now complete, they will soon die. Throughout the spring and summer, successive generations of monarchs, each living about 4 weeks, follow the milkweed as it grows progressively across the Midwest and into southern Canada. Then in late August, near a dairy farm in Minnesota or a lakeshore in Ontario, butterflies from a new Methuselah generation emerge, ready to undertake the Great Migration once again.
The series of steps that the monarch takes during this trip, both coming south and going north again in the spring, is truly astounding. Here's an insect moving by the billions between 3 countries. To imagine a tiny brain the size of a monarch brain being able to carry all the information that it needs to make this 2,500-mile trip, adjusting daily for the movement of the sun as it drops lower on the horizon, getting near the overwintering site in Mexico and somehow ending up in the same mountain range that their grandparents came from the previous spring. But that tiny brain puts all of this together. It is a wonderful mystery. It's going to attract scientists' attention for many, many decades or centuries to come. And we're only beginning to understand how miraculous this is.
It's impossible to look at a caterpillar turning into a butterfly and not ask how. Their metamorphosis, their migration, their life cycle. How did this happen? How is it regulated? How is it controlled? This astonishing, remarkable transformation. A biologist who encounters a puzzle like Metamorphosis is going to view that puzzle through an analytical filter, a lens. It's a way of trying to understand the problem. And for most biologists, that lens is going to be an undirected evolutionary process.
Since the late 19th century, most explanations for the life cycle of a butterfly or any other organism have shared a basic premise. To be considered scientific, they must rely exclusively upon undirected natural causes. This view was first published by Charles Darwin in his theory of evolution through random variation and natural selection. And today, it is widely accepted as a foundation of modern biology. But can such a theory account for the origin of metamorphosis?
On the evolutionary view of life, in particular on the Darwinian view of life, everything that an organism does, every feature that it has, all of its details ultimately relate to the requirements of natural selection. So to build the first butterflies, natural selection would have had to work entirely through genetic mutations. They're the raw materials of evolution.
A mutation is an error in the DNA of a living organism, an alteration of the genetic code. The theory of natural selection contends that the accumulation of mutations over enormous periods of time fuel the evolution of all complex life on Earth.
Generally speaking, mutations are mistakes. It's a change to the DNA, and these mutations happen in a random way. They're not guided or directed to happen in the right order, in the right sequence, in the right time.
There's no foresight involved in this process, no vision of what the organism needs in the future. Now, there's a real problem with that, especially when you consider the single most important element of metamorphosis, the chrysalis.
A butterfly chrysalis connects two fundamentally different ways of living. It is both a bridge and a workshop, where one type of organism is transformed into another. The magnitude of this transformation has been compared to a Model T Ford that suddenly encases itself within a garage. Inside, most of the car breaks down into fragments of metal, rubber, and glass. These pieces then reorganize themselves into components more complex than any that previously existed in the Model T. After several days, the garage door bursts open and a radically different mode of transportation lifts off into the sky.
Now, an analogy like that is pure whimsy. But even if it were somehow possible, I don't think turning a car into a helicopter would be nearly as impressive as the actual transformation that takes place inside a chrysalis.
From the moment the chrysalis is formed, caterpillar tissues are destroyed and then recycled to help build wings, compound eyes, reproductive organs, and navigational systems of stunning beauty and efficiency. Yet despite the importance of cell death in the chrysalis, the origin of the process defies the basic logic of natural selection.
One of the fundamental requirements of natural selection is reproduction. You've got to be able to make copies of yourself, in particular of your genes. You've got to be able to pass them on. But a chrysalis, unless it represents a bridge to something yet to come, is really a casket. If you're a caterpillar, you're entering your own grave. Turning most of your body into a molecular soup would be suicide.
A caterpillar, unless it makes it through to the adult, is no good because it can't reproduce. You're not going to have offspring, and so you're a dead-end street evolutionarily. So it wouldn't be any benefit at all to kill yourself unless you've got a hidden plan up your sleeve. You know, like, okay, I know I can go ahead and commit suicide because there's a new me waiting to happen.
The caterpillar is not going to enter the chrysalis without simultaneously knowing, I've got a plan for getting out of this. I'm heading towards the adult butterfly. I'm going to reconstitute these tissues in the adult form, emerge, and go on my way. But that's not how natural selection operates. It can't look into the future and somehow anticipate what an evolving organism is going to need in a week or a month or 1,000 years from now. So if the first caterpillars were evolving into existence, without foresight, it's highly unlikely natural selection would retain a destructive process like cell death.
This absence of foresight is not the only challenge to Darwinian theory. Biologists have long recognized that natural selection cannot succeed by taking large evolutionary leaps. Instead, the process can only move forward through a series of small, incremental steps.
In evolution, it's the smaller scale changes that have a better chance of being passed on because they're relatively limited in their scope. That means they're disrupting less, and they're more likely to be tolerated by the organism. But when it comes to the origin of metamorphosis, the notion of gradual evolutionary change comes to a dead end.
By its very nature, metamorphosis is an all-or-nothing proposition. And throughout biological history, its success is hinged upon the immediate availability of a full set of instructions, including genes, proteins, and the developmental program required to integrate them.
It all has to be in place ahead of time. It needs to have the genes in place, the regulatory elements that are going to turn the genes on and off. It has to have all the cells pre-programmed to do what they're going to do when the time comes, so they respond to the signals they get in the right way. The larval cells have to know they're going to die. You got to remember the caterpillar isn't thinking about things. It's not saying, okay, now it's time to dissolve my epidermis, and okay, what about that gut? Got to get working on that gut. No, it has to happen rapidly and in a coordinated fashion. Once you're committed to the chrysalis stage, there's no going back. You have to complete the transition.
A caterpillar that's equipped to go 10% or 25% of the way through metamorphosis is no way through metamorphosis. Part way into a process that requires getting out the other side as a fully formed adult doesn't work.
You have to recreate adult legs, adult antennae, adult eyes. You have to change the shape of the brain and the connections between the antennae and the eyes. You have to reformat the gut so that it switches from eating plant material to eating nectar. How many mutations does it take? And how do you coordinate all of that? If you get the eyes right, but the gut wrong, it's a failure as a butterfly. If you get the wings right and the legs right, but the muscles don't attach, that butterfly's going nowhere. It's dead. You begin to see the depths of the problem. So for evolution to have created this sort of pathway gradually, it would take a miracle.
Metamorphosis, if it came into existence at all by an undirected process, had to have done so in one fell swoop. Natural selection, by definition, I would say, cannot build that kind of process. To create a process like metamorphosis, you'd need a totally different type of cause. Something that could see a distant target, keep that target in focus, and provide all the resources necessary to hit the bullseye on the first shot. I think the only cause that could have accomplished that is an intelligent agent.
From a philosophical perspective, the suggestion of intelligent design as the explanation for the origin and development of life contradicts the assumptions of many biologists. But when considered objectively, evidence may be plentiful within the walls of a chrysalis or on a monarch's wings.
Metamorphosis not only challenges the Darwinian picture of life, in fact, it points in a positive way to the truth of intelligent design. If you saw a mechanical device of the sophistication of a butterfly, you would not for a moment hesitate to ascribe that to intelligence, because the butterfly is so much more sophisticated, almost beyond our comprehension, than anything that we make. Planning, foresight, artistry, engineering. Normally in our experience, when we see those criteria fulfilled, or we see those indicators, we say that's positive evidence of intelligent design. To build a butterfly, you need a cause that can visualize a long-range objective and then direct every step of the process that's required to make it happen. Only intelligence, universally in our experience, is capable of doing that. You also need a cause that can reuse lower-level component parts to construct a different, higher-level system. For butterflies, the same genes and proteins that build you a caterpillar can be reused to give you an adult flying insect. As Nobel Prize-winning geneticist Barbara McClintock noted, it's astounding that two brilliantly designed organisms share a single genome. To build a butterfly, you have to be able to assemble a network of elaborate substructures like wings, navigational systems, and a proboscis, and then integrate all these systems into a very complex organism. And you need a cause with an artist's eye for color and pattern and shape. A sense of beauty and aesthetics that extends way beyond utilitarian purposes like camouflage or species recognition. There may well be in butterflies aspects of beauty that are there not for the sake of reproduction or survival, but for us to appreciate.
A lot of people I know who study biology do it because they find it beautiful Natural selection has no reason to produce beauty. Beauty is a sign of the transcendent. It's purely gratuitous. We all recognize it. We just have to acknowledge what it points to.
As human beings, we have a unique gift that enables us to evaluate evidence and then arrive at logical conclusions. That's what science is all about. When you see certain effects in nature, it's your responsibility as an investigator to find the cause that will explain the effect. When you process all the evidence revealed through Metamorphosis, and then you ask yourself, in your own experience, what kind of cause could bring about these results? I think the only reasonable answer is an intelligence that transcends the natural world. A designer with foresight and a sense of engineering and artistry, and the ability to light up the sky on a summer afternoon with magnificent evidence that life on Earth is the product of something greater than a blind, undirected process.
They were first discovered in 1975, January, by an American couple based in Mexico City. They had been searching for many years for the monarch's winter home, following Fred Urquhart's request from the Royal Toronto Museum. He had been marking butterflies for over 3 decades, knew that they disappeared as they approached the southern boundary of the U.S., hypothesized they overwintered somewhere in Mexico, but had no idea where. So Ken Brugger and his wife went out every weekend on motorcycles, and in January of 1975, they discovered the monarch's winter home near Angangeo, Michoacan. The butterfly actually is a tropical species. It never, as far as we know, existed in North America as a resident species. It cannot stay here 12 months a year because it has never adapted in any of its 4 life history stages to surviving freezing or below freezing weather. So it's a tropical butterfly. In Mexico, it has several competing species that feed on milkweed. In Mexico, there are only 6 species of native milkweeds. In the United States, north of the Mexican border, there are 108 species of milkweeds. So there's a bonanza of food to the north of the border that it can occupy and use seasonally as a larval host, just like migrating warblers come up to breed in our forests from the tropics because there are lots of insects there seasonally, or the ducks fly all the way to the Arctic, 10,000 miles from Argentina, to find a bonanza of aquatic insects and pond weeds to eat for a couple of months, and no competition, or little competition, compared to what they face in the tropics. So the monarch comes north to breed, does a great job, produces billions of monarchs by the end of the summer, from several hundred million that maybe have made it north, and then flies south again to overwinter. With regard to the Methuselah gene complex, that probably is turned on by the same biological clock mechanism that detects this change in day length for the reproductive status of the butterfly, so that those genes that respond to the biological clock include probably both the Methuselah genes that tell that 4th generation it's got to live 9 times as long as the previous 2 or 3, and also the genes that are going to prepare the reproductive organs to shut down, save energy, devote all that into flight muscle and stored energy in the abdomen, fats, and ignore the needs of reproduction, because after all, there's not going to be any milkweed satisfactory condition for the next 5 or 6 months. So you don't need to waste energy keeping up courtship and trying to produce eggs for no purpose. Better to shut all that down, devote all your energy to survival for the next 5, 6 months. Basically, every butterfly in the monarch species east of the Rocky Mountains Continental Divide flies south or southwestward to reach the Mexican border by late fall. So the ones in Canada will start in late August, early September. The ones in New York might start in mid-September. Ones in Georgia might not start till the end of October, early November. But they all make it to the state of Tamaulipas, right across the border from Texas, and there they cross onto the central Mexican desert plateau and then fly due south through the desert. And there they take advantage of all the flowers been brought up by the late summer, early fall rainstorms from tropical storms sweeping across the Gulf of Mexico. Circadian means about a day, circa diem. So circadian means that most organisms are able to keep track of a 24-hour cycle. And they do this by a biological clock mechanism. Not too hard to figure for a human or a whale or a marmot or something with a pretty big brain and lots of things going on, lots of cues. But for an insect to keep track of a day, it's pretty remarkable. Yet most insects do. They may be active for only an hour during the day. Mayflies, for example, fly just at midday to mate and reproduce, and other insects may fly only at dawn or at dusk. Others may fly at 10 o'clock at night. Saturnid moths fly at 3 in the morning. So the monarch's circadian clock was long thought to be in the brain, like many other insects. But recently, last year, in fall of 2009, it was discovered by scientists that the circadian clock in the monarch is actually in the base of the antenna, just a short distance from the head. And the sensory organs embedded in the antenna somehow detect and keep track of the amount of time going off each day. And they keep this going in constant darkness or constant light, doesn't matter. They're entrained to keep this going. And this is very important for keeping track of day length or keeping track of when you're supposed to become active in the morning or whatever. In the human brain, we have something like 10 billion neurons and an incredible number of connections between them, at least 5 or 6 between every pair of neurons. In the monarch brain, we're talking about several thousands of neurons, and yet somehow it packs into its brain a better navigation system than we have as humans. We have to invent a technological marvel, a GPS system, to enable us to find our way in a crowded city where all the streets are marked with signs and houses have numbers and all this stuff. The next time you fly in an airplane, look out the window and discover how on earth would you find your way from New York to South Carolina or Georgia if all you had was the ability to look out that window from the air and see all these patches of ground. You'd have no idea where you were. If there were no landmarks that you were familiar with, like the Great Lakes or the Mississippi River or something, you'd have no idea where you were or what to do. Yet somehow the monarch does this. And we've discussed some of the navigation mechanisms, but that tiny brain puts all of this together and cues each thing in at the right time in the right place to make sure it gets up to the right end point, down deep in the tropics in southern Mexico. The question is how the butterfly figures out what direction to go. If it's up in New York, it's going to fly southwest. If it's in northern Florida, it's going to have to fly almost due west to reach the same goal, Brownsville, Texas, say, and crossing in Tamaulipas. So we don't know yet whether butterflies from a particular colony in Mexico return to the same place they started, or at least the same direction they started. So, for example, we don't know yet whether the butterfly that flew from New York southwest to Mexico got to the colony, then survives the winter. If she then turns around, flies north, gets to the Texas border, and takes off on a northeastern trajectory towards New York, and then her progeny keep following, leapfrogging up to New York. That would be a wonderful situation, because then we could say, oh, they're genetically programmed. All the ones from New York are going to end up this site in Mexico and then go back to their progeny will go back. If we move one from New York to northern Florida and put it in a big cage, it will try to fly southwest, though that would take it right down into the middle of the Gulf of Mexico, and it probably wouldn't survive trying to cross from there to Tabasco or Veracruz. So, because it would be too long a trip across open water. So no one knows yet exactly how they do it. What is known is if you take some migrating butterflies in Kansas and you put them in a big cage, they try to go to the southwest direction to Texas. But if you surround that cage with electromagnets and turn on a new magnetic field that's stronger than the Earth's magnetic field, you will screw them up totally. They will start flying north. They'll start flying exactly the wrong direction. You just keep moving that magnet around, and they react to it and orient from that and get all messed up in their migration. So the magnetic detection of magnetic fields apparently is important earlier in the migration than just at the end as they find the transvolcanic range. But what the relationship is between that magnetic compass, the sun compass, and all the other things that are going on, no one knows yet. They know where the sun is in relation to their position each morning, and that seemingly drops further and further south in the horizon to the southeast, where it comes up to the southwest in the spring, because the sun's lower and lower in the tropics. It's going on down to the Tropic of Capricorn while all this is going on in the fall. So they're moving south, following the sun's directions, and they're adjusting their flight each day. What they can't do is if they're moved a whole bunch by an airplane, and then figure out where they are again and start all over. So apparently where they start has an important role in setting the direction that they're going to follow. From the day they hatched from the pupa anyway and flew around that area, something imprinted on them that that's where they are, and to get from where they are to this place in Mexico, they've got to move at a certain angle. But no one knows how that's done yet. I mean, what we've discovered so far is miraculous enough. To reach that nirvana of accomplishment will require another generation or two of scientists. Most of the migratory movement for the greater distances is by gliding. Monarchs have a very strong gliding flight. They can fly up to several thousand feet, even 10,000 feet in the sky above the land, and pick out the wind currents that are moving them in the desired direction. So they don't stay at a particular elevation where they'd be fighting a strong westerly wind. They look for another band of air that's moving in the right direction for them. They've been known to travel up to 350 miles or so in a day if they have a strong tailwind. And their wings are incredibly flexible. We've just discovered here at the McGuire Center that the monarch wing actually can form cups and little valleys between the veins, and the monarch somehow has control over how these veins can be flexed and moved, and take every possible advantage of a breath of air to save their energy on this flight and move as much as 40, 50 miles a day to the southwest to Mexico. Well, the first butterflies start moving south at the end of August, 1st of September, and they are up in northern U.S. or southern Canada. That they will reach the site on about November 14th or 15th. Surprisingly, it's very precise. You can be there in Mexico, not see a butterfly on the 13th, and on the 15th, all of a sudden, the first few dozen show up. And by the 20th of November, there'll be hundreds, and then thousands, and then millions, and then hundreds of millions, such that by the end of November, first week of December, they're almost all there. The monarch's well adapted to survive bird attack. Its wings are kind of leathery. They resist tearing and that. The scales stay on pretty firmly. The body is equally flexible so that a bird touching it or grabbing it with its beak can't do too much damage before it tastes the chemical and releases it. So that pretty well adapts it for a long-distance migration as well. The monarchs arrive on the colony site looking quite fresh, like they had just emerged from pupa in many cases. Others arrive pretty tattered. We assume they've been through major storms or battered about in the forest by winds, and maybe even attacked by birds or lizards. They survive the trip and get there. Birds and other natural hazards can remove as much as half of the wing of a butterfly, and the butterfly can still fly successfully. The monarchs have reached a place that was a satisfactory overwintering site the previous year for their grandparents and great-grandparents, and that's a pretty safe starting place. But the next few nights, they'll adjust their position on the mountain by the temperature. If it's too cold, they'll move down the mountain. If it's too warm, they'll move up the mountain. The whole idea is to reach a site where temperature's just above freezing day and night, so the butterfly doesn't have to fly, no activity, just burning its stored reserves very slowly, and survive the whole winter that way. But if there's global warming or some problem like that coming along, then the whole colony moves up the mountain as much as several miles, or it may move down the mountain if a fierce winter storm comes in from the Pacific. It's like a mercury and a thermometer adjusting to conditions that we can only imagine adjusting to. But here's this butterfly, no ability to put on a fur coat and can't adjust the number of scales on its body. Instead, it has to adjust its position on the mountainside and in the orientation that it takes on the tree. Apparently, day length increases to 12 hours, and right at about 12 hours around the Ides of March, wonderful things begin to happen. In the monarch colony is that the reproductive organs are stirred to get active and start producing sperm and eggs, just in time for them to mate and send fertile females north again ready to lay eggs. The males go with them. Males probably fly north for several reasons. First of all, they can have another chance for sex because a single male can mate 6, 7 females during its lifetime. But second, you've doubled the number of monarchs in the air. So a naive bird, a young blue jay or mockingbird or something that's trying its first food in the form of a butterfly, if it picks that bright orange butterfly, it has about a 50-50 chance of grabbing a male. And the male will work just as well as the female, teach a naive bird to leave it alone because it has poisonous compounds in its wings, and the bird tastes that, has a very strong emetic response, begins vomiting, and remembers that the rest of its life. Doesn't try that bright orange monarch again. So the fact that the males are migrating with the females offers some protection to the females. They're only handled by birds in that half as often as if they would be if only they moved north. A single female could lay over 450 eggs, maybe 500 eggs. So if they live for a month or so in the southern U.S., they can lay hundreds of eggs, maybe 10, 15 a day on milkweed plants. And even if they've been greatly reduced in numbers during the winter by a storm, they can bring back the monarch population pretty rapidly by having a couple generations, each laying hundreds of eggs per female. When the monarch leaves the overwintering site in mid-March, it takes a couple of weeks for it to reach northern Mexico and cross into the southern U.S. At this point, in early April, the milkweed species that grow in southern and central Texas are just coming up above the ground. The first 2, 3 leaves are there, maybe it's 4 or 5 inches above the soil, perfect for a milkweed to lay eggs on. It takes a week for the eggs to hatch. By then, the milkweed's up to maybe 10 leaves above ground, and there's plenty of food for the developing caterpillar to eat. When it flies further north as a new adult, a month later, it finds another species of milkweed, and it's just coming above the ground. So forth all the way up to Canada, where the milkweed plants come up in late June or early July, and monarchs arrive there at the right time to get them. They're following the milkweed. It's like following a green carpet that's gradually coming up, and it's coming up first in the south and in the central states and in the north. It's very important that there be thousands of milkweed plants per square mile to really get effective reproduction, and that's why the central United States is so important to the monarch. In the prairie states, where we have great crops of corn and soybeans and so forth, milkweed plants used to occur by the millions in these fields, and they'd survive along the edges of the field or in among the corn plants, and everything was fine till about 10 years ago. And then, unfortunately, a chemical company, Monsanto, developed a herbicide-resistant gene that could be put into corn plants and soybeans, and that meant now all of a sudden a farmer could be encouraged to spray his cornfield or his soybean field with weed killers, herbicides, that would kill not only weeds that you didn't want, but also the milkweed plants, the food plants of the butterflies. And so it's a disaster now, because 95% of our American corn crop, nearly 100% of our soybeans, are herbicide-resistant hybrids. And that means the death of the monarch in all those fields, because milkweed plants can't survive there. Well, here's a monarch butterfly, that species that we've known for over 500 years in colonial America up to the present time. It's been proposed as our national butterfly in Congress. It exists in every state in the Union, even Hawaii. It's a symbol of spring. It's a symbol of resurrection to many people. It's a symbol of survival to others that know something of this remarkable story. You have to ask why save the Mona Lisa? Why save other unique works of art in that? Well, here's a butterfly species that does something truly spectacular, something the U.S. Navy can't do, or the Air Force or whatever, to navigate with just the sun and so forth to such an incredibly precise location, and then come back again and do the whole thing over again the next year with a generation that skipped 3-4 life cycles. We're only beginning to understand how miraculous this is and how things like the Methuselah genes could benefit mankind. So my question is, why lose it? Let's try to save it. Here's something that can inspire people and be a symbol, a flagship for conservation, for the usefulness of all life, not just the big fat cows or 12 food crops, grains that we live on, but something that could be important as a symbol. I think every human should, if at all possible, have the chance to stand in a monarch colony on a winter day when they all take flight at once as the sun comes out and they are readjusting their location, and to just stand there quietly, hear nothing but the fluttering of millions of wings, watching billions of loose scales come down and cascading in the sunlight. That's an incredible experience. You'll never have anything like that in your entire lifetime. I've seen people take out a Bible and begin reading it there. I've seen people with tears in their eyes, just moved by the whole experience to the point where they can't express what they've seen. It's something that everyone should have the chance to experience. And here in the United States, we have a few colonies along the California coast, which are pretty large, up to 10,000 or so. But just imagine 300 million monarchs in one site, all taking flight on a sunny day and a crisp, cool Saturday, and having that experience of something that has flown 3,000 miles to get there.
universe we observe has precisely the properties we should expect if there is, at the bottom, no design, no purpose, nothing but blind, pitiless indifference.
I don't know, I'm pretty satisfied with the explanation of the evolutionists.
Yes, I do believe we are descended from animals.
Evolution is obvious.
Man was not created in God's image. God was created in man's image in order to address those things about which we were ignorant.
I think part of the grand joke of it all is that, before there was feet, there was flippers. Before there was lungs, there was gills. And, it's all part of that process that got us where we are today, gridlocked and angry.
I sometimes wonder why anybody talks about anything else, because this is the most interesting topic there is. Where do we come from? How did we get here? What brought us into existence? What is our relationship to reality as a whole?
You look at the incredible diversity and complexity of life, and inevitably the question arises, what brought all this into existence? Was it simply chance and necessity, undirected natural forces? Or is there something else going on? Is there a purpose, a plan, a design due to an intelligent cause?
It's really interesting to notice that the more we know about life and the more we know about biology, the more problems Darwinism has and the more design becomes apparent.
We have not the slightest chance of a chemical evolutionary origin for even the simplest of cells.
The discovery of the information-bearing properties of DNA and RNA is a fundamental challenge to all materialistic theories of the origin of life. Neo-Darwinism and its associated theories of chemical evolution and the like will not be able to survive the biology of the information age, the biology of the 21st century.
When I look at the evidence objectively, without ruling out the possibility of design, design just leaps up as the most likely explanation. And that's why I believe that it's true.
We can't explain these systems by natural law. And if we're searching for truth, and they are in fact designed, if we have to be design engineers to understand them, then I say, what's the problem? You go where the data leads you. And the implications, yeah, they have profound metaphysical implications, but so be it.
For several centuries, we've been told that the universe does not have us in mind. That is, that we exist in a small speck of dust in a very large universe, and that the universe was not designed for beings like us. Our argument suggests something completely different. It suggests that the universe was intended, that the universe exists for a purpose.
The laws of physics are balanced on a razor's edge for life to occur. What you have is a universe that is not only finely tuned for life to occur, but also has a beautiful, elegant mathematical structure, and a structure such that we can discover that structure.
There's something about the universe that can't be simply explained just by the impersonal forces of nature and atoms colliding with atoms. And so you have to reach for something beyond the universe to try to account for it.
The founders of modern science, like Copernicus and Kepler and Galileo and Newton himself, believed that the universe was the product of a mind, that it was intelligible to beings like ourselves because the universe itself was the product of an intelligent being.
I was trained in journalism and law to respond to truth. I had to take a step of faith in the same direction that evidence is flowing. You don't have to commit intellectual suicide to come to the conclusion that there is an intelligent designer. Because today, science is pointing more directly and more powerfully toward a creator than any other time in the history of the world.
We have not the slightest chance of a chemical evolutionary origin for even the simplest of cells. So the concept of the intelligent design of life was immensely attractive to me and made a great deal of sense, as it very closely matched the multiple discoveries in molecular biology.
In the years since Kenyon's rejection of chemical evolution, science has revealed the details of an entire system of information processing that bears the hallmarks of intelligent design. With computer animation, we can enter the cell to view this remarkable system at work. After entering the heart of the cell, we see the tightly wound strands of DNA, storehouses for the instructions necessary to build every protein in an organism. In a process known as transcription, a molecular machine first unwinds a section of the DNA helix to expose the genetic instructions needed to assemble a specific protein molecule. Another machine then copies these instructions to form a molecule known as messenger RNA. When transcription is complete, the slender RNA strand carries the genetic information through the nuclear pore complex, the gatekeeper for traffic in and out of the cell nucleus. The messenger RNA strand is directed to a two-part molecular factory called a ribosome. After attaching itself securely, the process of translation begins. Inside the ribosome, a molecular assembly line builds a specifically sequenced chain of amino acids. These amino acids are transported from other parts of the cell and then linked into chains often hundreds of units long. Their sequential arrangement determines the type of protein manufactured. When the chain is finished, it is moved from the ribosome to a barrel-shaped machine that helps fold it into the precise shape critical to its function. After the chain is folded into a protein, it is then released and shepherded by another molecular machine to the exact location where it is needed.
This is absolutely mind-boggling to perceive at this scale of size such a finely tuned apparatus, a device that bears the marks of intelligent design and manufacture. And we have the details of an immensely complex molecular realm of genetic information processing. And it's exactly this new realm of molecular genetics where we see the most compelling evidence of design on the Earth.
a lot of things went right on Earth to have yielded complex life, absolutely.
The number of factors that have been postulated has grown. Currently, the typical number you would see is, in a typical list, would have something like 20.
We find that we need to be at the right location in the galaxy, that we're inside the circumstellar habitable zone of a star, that we're in a planetary system with giant planets that can shield the inner planets from too many comet impacts, that we're orbiting the right kind of star that's not too cool or not too hot, that we're on a planet that has a moon that can stabilize the tilt of its axis, that we're on a planet that's a terrestrial planet, a planet that has a crust that's just thick enough that it can maintain plate tectonic activity, that has enough heat in its interior that it's still circulating its liquid iron core so it can generate a magnetic field, that has an atmosphere that has enough oxygen to allow for complex organisms to survive, that it has enough water and enough continents to allow for the diversity of life for an active biosphere that you need to support complex creatures such as ourselves. All these factors have to be met at one place and time in the galaxy if you're going to have a planet as habitable as the Earth, which you need for complex and even technological life.
In an attempt to estimate the probability of attaining this combination of factors simultaneously, some researchers have developed equations assigning a conservative 1 in 10 value to each factor deemed necessary for advanced life.
If every element has to be there at the same time, you have to multiply the probabilities, and that's what makes the probability at the end so small. You've got 10% of this and 10% of that, and these things rapidly multiply to exceedingly small numbers. The numbers on the order of 10 to minus 15, which is 1/1000th of 1 trillion. And it's a number like that that you have to compare to the 100 billion stars that are in the galaxy. 100 billion is a very large number, but 1,000th of a trillionth is much, much smaller. On their face value, these probabilities are speaking. What they're telling us is this can't happen, or this is very unlikely to happen in the galaxy. And that's where the evidence is pushing us.
There are many probabilistic resources in the galaxy, but on the other side of the coin are all these factors that you need. You have to get just right in order to have just one habitable planet like the Earth. And that leads me to conclude that yes, we're rare in the galaxy.
An ancient mystery is etched upon these mountains. A story of primordial oceans and prehistoric life, of creatures stranger than fiction, and the controversy that has surrounded them for more than a century. Buried among these majestic peaks are glimpses of an event that transformed the planet in a moment of geological time. Compelling evidence, etched in stone, that challenges long-held assumptions about the origin of animal life on Earth.